Welcome to this section. Now let's look at some fire definitions then. Definition. Flash point. The flash point or flash ignition temperature is the lowest temperature at which a substance produces enough vapour to produce a momentary flash upon the application of an ignition source. And some examples that you might remember is diesel is plus 40 and petrol is minus 40. So let me explain what the flash point is. If I've got some diesel, which is the flash point is 40 degrees, if I heat diesel up in a cup to say 20 degrees in a room and I put a match above it, what will happen? Nothing. In fact, why? It's the molecules are not reacting now. It is giving vapours off all the time because you can smell it, but it's not giving enough vapours to flash. If I heat it up to 35 degrees and put a match above it, what's going to happen? Nothing. It won't flash. In other words, although it's giving off more vapours, there's not sufficient vapours to burn. If you heat it up to flash point, 40 degrees, heat it up the diesel, now put a match above it, it will flash momentarily. So it goes bang, but it will not continue to burn. There's enough vapours to flash, but not continue to burn. That's where the next definition comes in, fire point. Now the fire point is the lowest temperature at which a substance produces enough vapour to flash upon application of an ignition source and continue to burn. So which has got to be the higher temperature? The fire point. The fire point's got to be a higher temperature, a few more degrees. In other words, you heat it up a bit more and it gives off a few more vapours. Now it can continue to burn. Now, these definitions are very important when you're talking about flammable liquids because you can appreciate how to store them and handle them more. Say you brought a new flammable liquid in the workplace and you looked at the safety data sheet and it says the flash point of this liquid is minus 100. What are you thinking? Minus 100? I'll tell you what, if that lid's taken off there, the vapours are out, you have created an explosive atmosphere. Who ordered this? That's why they say try and get liquids with high flash points. They're a lot safer, like diesel. Now, if you take diesel to Cyprus on a hot day, 40 degrees flash point, and it's 42 degrees, you have to handle diesel the same as we have to handle petrol in this country. Do you understand? It's important of what temperature it is. Now, this video here demonstrates that even professionals can get it wrong. This guy here is trying to set fire to a boat as part of a training exercise. The idea is he's going to set fire to it and a boat's come along and putting it out. Now what he's throwing on there is petrol, not diesel, petrol. It's got a very low flash point. The vapours have been given off. Now, if you want to look away, now is the time to look away. I am warning you. Just if you want to look away, now's the time. Bang. Now he's not injured. He's not injured. He's got full protective clothing on. He's not injured. You'll see in a minute. There he is. Jumps out on the boat. He's not injured because he had full protective clothing on. Well, someone said to me, why did he do that then? Because he's an idiot. Why would you set fire to put petrol on a boat and light it like that? Someone said to me, why? And the cameraman thinking, is that a good idea to do that? That's because he was using petrol, which has got a low flash point. As soon as you pour it out, it's giving off the vapours. The next definition I'm going to explain is auto-ignition temperature. So what is the auto-ignition temperature? Well, this is the lowest temperature required to cause self-sustained combustion in any substance in the absence of a spark or flame. Or another definition, basically, it's the lowest temperature which a substance will automatically ignite in the absence of a spark or flame. So let me explain this. For example, cooking oil. Cooking oil. You've got some cooking oil on the pan, you're heating it all up, and say the flash point's 40 degrees, the fire point's 45, and the auto-ignition temperature's 450. You start to heat the cooking oil up to 35 degrees, you put a match above it, what happens? Nothing. You heat it up to its flash point, 40 degrees, and you put a match above it, what happens? It flashes. Does not continue to burn. You heat it up more, you heat it up to its fire point. What happens to the cooking oil? If you heat it to its fire point and put an ignition source, well, it now ignites and it'll carry on burning. However, you've got no matches on you. You keep heating the oil up to 450 degrees. What's happening in the oil? Well, what's happening to these bonds? Well, they're trying to break, but they've no ignition. Now, when a substance reaches auto-ignition temperature, it's got so much heat energy that eventually one of those bonds will break on their own. Now, once you've got the first two radicals, what happens? Well, it's a radical chain process. In other words, now you don't need the ignition. You've given it enough energy to start the combustion process. You've got an exothermic reaction, and that is auto-ignition temperature. Right, what is the last thing you should use to get a bonfire going? Have a guess. Petrol? Watch this. These two guys here, he wants to set fire to a bonfire. What's he using? Petrol. This is petrol he's using. It's not a good idea. You shouldn't use any accelerant to get it going, but you definitely don't use petrol because petrol has got a minus 40 degrees flash point. Some people use paraffin. Now, has he put enough petrol on, do you think? Has he put enough petrol on? He's even making a fuse. It's not gunpowder, it's petrol. What is surrounding that whole area? Vapours. Because it's got a low flash point, all the vapours have been released. He's getting an explosive atmosphere. Now, he needs to finish it off, and he won't do that anymore. It's too expensive. Anyway, if you want to look away, now is the time to look away. No one's injured, but I am warning you, if you want to look away, was that a wise thing to do? What have we got left? That's what happens if you use petrol. Yeah? Can you imagine that? Your wife says, have you burnt all that wood? It's all gone. It's all gone. The next issue we're going to look at is vapour density. This is the vapour density. Now, what is vapour density? Well, it's the density of a gas or vapour compared to the density of hydrogen. That's what you need to remember. Its vapour density is compared to hydrogen. Why do they compare it to hydrogen? Because hydrogen is the lightest element. It's the lightest element in the periodic table. And the vapour density is determined by using the molecular weights of the atoms concerned. Now, as you can see from this periodic table here, the molecular weight of carbon is 12. The molecular weight of nitrogen is 14. Molecular weight of oxygen is 16. So, the vapour density of, say for example, methane, let's work it out. CH4. The carbon molecular weight is 12. Hydrogen is 1 and there's 4 of them. So that gives you a molecular weight of 16. Well, the molecular weight of hydrogen is 2 because there's 2 hydrogens. So that gives you 16 divided by 2. The vapour density of methane is 8. Methane is 8 times heavier than hydrogen. So that's the vapour. Now the problem is, this doesn't actually tell you a lot because air is not just made up of hydrogen. What you want to know really is how heavy is that gas compared to air. And this is why we move on now to relative density. Now the relative density of a vapour compared to air, this is what relative density is. It's comparing it to air. Now this is important because it tells you that if it's released, is it going to go up or down? In other words, what ventilation do you need? If it's lighter than air, it's going to go up. If it's heavy, it's going to go down. What are the ventilation requirements? Now, lead-acid batteries emit hydrogen. So charging these batteries emits hydrogen. Where should you need the vent? Well, it depends. If hydrogen is the lightest element, where's it going? Up. So where do you need the ventilation? In a charging area for batteries, you need high-level ventilation. Don't let it accumulate. I went to a chemical company that processed hydrogen. And it was an outside plant, massive plant. And the guy said to me, if we get a release of hydrogen, we're really, really worried because all the ignition sources, because it's a highly flammable gas, it's hydrogen. I said, yes, but the vapour density of hydrogen is 1 because you compare it to hydrogen. In other words, if that is a leak of hydrogen gas, where's it all going? Well, up very quickly. There'll be nothing coming this way. It's all going up. What I'd be more worried about is the flight path of an aircraft. If an aircraft flew over a cloud of hydrogen gas and it got in the chamber, you're going to have an explosion. So what I'm getting is vapour density and relative density are very important. Now, one number you need to remember is the relative density, the molecular weight of air, or relative, is 28.8. That's the molecular weight of air. It is approximately 28.8. Do you think oxygen is heavier or lighter than air? What do you think? Heavier or lighter than air? Well, let's look on here then. The atomic number of oxygen is 16. The molecular weight of oxygen is 32. Well, it's heavier then, isn't it? Air is 28.8, oxygen's heavier. If you get a cylinder of oxygen, you open it up and you release it, the oxygen will go down. It will settle down because it's heavier. So again, where do you need your ventilation if you're going to try and get it low below? CO2, is it heavier or lighter than air? If I set off a CO2 cylinder in here, is it going to settle high or is it going to settle low? Well, let's look. CO2, carbon is 12, oxygen is 16. So CO2 is 12 plus 16 plus 16, 44. CO2 is heavier than air and it will sink and it will collect down low. So CO2 is heavier. What about methane? Is methane heavier or lighter? Think of methane gas, like a sewer gas. Let's have a look. CH4, carbon is 12, hydrogen is 1, so methane is 16. It is lighter than air. So that's going to, where's that going to collect? Up high. So you need high level ventilation. One more. Is acetylene heavier or lighter than air? C2H2. Well, carbon's 12, hydrogen's 1. That makes it 22, 24, gives you 26. Acetylene is lighter than air, but only slightly. Air is 28.8. Acetylene is 26. In other words, it's going to mix very, very well. And it's a very volatile gas, is acetylene. So where should you store acetylene cylinders? Outside, in cages, well ventilated, away from buildings, away from ignition sources. I turned up to do some training at a foundry. And when I arrived at this foundry, I'll tell you what, it was like walking into hell. That's the only way I can describe it. You walk in there, there's forklifts flying around, health and safety, I'm not happy. I walk in, there's 20 CO2 extinguishers empty on a wall right next to me. And I walked in, I said, what? I said to the manager, I said, what are those for? He says, they're for all the fires we get. This is a foundry, mate. We get fires in foundries. I said, well, what fires will you get? He said, well, something will spit out the furnace and set fire to some rubbish. So our guys put it out with an extinguisher. Well, what does that tell you? Poor housekeeping. That was the problem. It was, there's no housekeeping rules. Anyway, I walked in the foundry. Big foundry, furnace is burning away. I looked in the corner, there's 2 acetylene cylinders being stored in the foundry. And I said to this guy, I said, hey, you know, why are you storing acetylene in the foundry? He said, this fire guy said it was all right. Did he? Have you got his name? Oh, told you it's all right to store them in here. He said, look, they're stored upright, which I like, and they've got yellow lines painted round them. I says, all right, I never saw them. Oh, you're all right. Because if that acetylene leaks and it sees the yellow lines, what's it going to do? Oh, I shouldn't go past them, should I? What's that got to do with it? If that acetylene leaks, C2H2 leaks, that cylinder, what's it going to do? It's going to mix really well with the air. And when it travels across the foundry and it reaches the furnace, what's going to happen? An explosion. The foundry. You do not store acetylene cylinders in foundries. You might use them with hot work permits if you have to, but you store them outside the foundries. Next thing I'm going to talk about is vapour pressure. All liquids and solids have a tendency to evaporate to a gaseous form. And all gases have a tendency to condense back into their original form, whether it's a liquid or a solid. So do you see what's happening? It's a state of a rotation. At any given temperature for a particular substance, there is a pressure at which the gas of that substance is in dynamic equilibrium with its solid. In other words, it's getting just as much off as it is in. So in other words, it's vaporising, condensing, and it's keeping the same structure. This is the vapour pressure of that substance at that temperature. Now, this equilibrium vapour pressure is an indication of a liquid's evaporation rate. In other words, how fast it's going to evaporate, and it relates to the tendency of the particles to escape from the liquid or solid. A substance with a high vapour pressure at normal temperatures is often referred to as volatile. So that's the importance to you. The vapour pressure is an indication of how volatile that particular substance is and what it's going to give off. Now I am going to discuss the flammable limits, which will have a serious impact on how you store flammable materials in the workplace. So what is the flammable range then? The flammability range is the range of percentage of vapour or gas concentration by volume in air between the upper and lower limits of flammability. So it's the range of the lower and upper limits, that's the flammable range. Some have got wide flammable ranges and some have got narrow flammable ranges. But it's always the percentage of the vapour in air, not air in vapour, it's the percentage of air in vapour. Now, there are two limits, namely the LEL and UEL, which is the lower explosive limit and the upper explosive limit, and these are interchangeably with the LFL and UFL, which is the lower flammable limit and the upper flammable limit. They're the same principle actually, but it's LEL, UEL, LFL, UFL. The mixture will not burn when the composition is lower than the flammable limit or higher than the upper flammable limit. So you've got to be between the lower explosive limit and the upper explosive. Those percentages, it's got to be between those concentrations to burn when an ignition source is applied. So let's go again, the LEL. This LEL is the lowest concentration of fuel vapour when mixed with air that will burn when an ignition source is applied. And the upper explosive limit is the highest concentration of fuel vapour mixed with air that will burn when an ignition source is applied. So there's the lower explosive limit and the upper one. Let's explain this then. An example, an arsonist walks in a room with a little can of petrol and he pours it in the corner. Petrol's got a flash point of -40, so straight away the vapours are being released. He comes along to the corner of the room, the vapour starts to get to him, and the LEL, the lower explosive limit of petrol, is 5%, and the upper is about 12%. So that's the flammable range of petrol, between 5 to 12%. Now he comes along, the vapour starts to come to him, he gets a match out, and he lights a match when the petrol vapour is 3% in air. So there's 3% of petrol vapour. Will it burn? No. You've not reached the lower flammable limit. Okay? So, he leaves it a bit longer. It gets to 6% vapour where the match is. And he lights a match. Will it burn? Yes. Because it's between the 5 to 12%, it will burn. And what you'll see is as he lights it, the flame will go straight back to the container and the liquid will burn. That's it. Now, that's how the flammable limits work. Now, what happens if this arsonist is a real bad one? He brings in 50 gallons of petrol and he pours it in the room. And he fills that room with 25 to 30% petrol vapour in air. So there's at least 30% petrol in the air. And he tries to light a match. Will it burn? No. You've gone outside the limits. It's not. You've gone above the upper explosive limit. That's what this is all about with the flammable limits. Now, on the same point with these flammable limits, what happens if you've got an atmosphere fully between the LEL and UEL? So you come in here, you put in 5 gallons of petrol, you let it vaporise, and the whole room is between the flammable range. So the whole room has got an atmosphere between 5 to 12%, and you light a match. What will you experience? An explosion. Do you see what's happening? The whole room explodes because the whole room is between the LEL and LFL, whereas if only part of it is, you'll see a fire when it goes back to the cylinder. That's the difference. That's the difference. Look at this table here. The flammable limits of petrol about 5 to 12%. Acetylene is 2.5% to 80, something like that. So acetylene is a very volatile gas. Hydrogen is 4 to 74, depending on which data you look at. Carbon monoxide, which is a flammable gas, a product of incomplete combustion, is 12.5% to 74, so that's quite wide. Methane, 5 to 15, not a very volatile gas. Acetylene, 2.5 to 80, so there's another volatile gas. The wider the limits, the more volatile the gas is considered to be. Now these limits, these flammable limits, are in air. What happens if you increase the oxygen concentration? What happens to those flammable limits? Well, they're widened. If you increase the oxygen, as you increase it, it widens the limit. It makes the gas more volatile. And eventually it gets to the point where any gas in the atmosphere will create an explosive atmosphere. What happens if you inert an atmosphere? You pump in nitrogen. What happens to the flammable range when you start to inert an atmosphere? Well, they get narrower and narrower and narrower. And in the end, if you fully inert a gas, there's no flammable range. It's gone out of it. Do you see how oxygen concentration increases the flammable range? Inerting decreases the flammable range until combustion ceases. Now, how do you tell if an atmosphere is explosive? We can get an explosimeter. This is an instrument that's used to determine the quantity of gas in the atmosphere. For example, if you're looking at LEV, local exhaust ventilation requirements, the person will normally take in an explosimeter and take samples of the gas to see if an explosive atmosphere is created. And in fact, in the fire brigade, we have explosimeters. Say, for example, we're called to an incident and there's been a gas release, like, for example, acetylene. We have to work out if it is an explosive atmosphere, and we'll take in this explosimeter. What an explosimeter does in simplest form is it draws in the atmosphere and it attempts to burn it. You have to select the gas you're looking for. You can't just say any gas. You have to select it, and say you set it as acetylene, go in the atmosphere, it draws it in and it starts to beep and it goes out. Now you go in there and it says 10%. 10%. What? 10% of what? Well, it's not 10% acetylene. You are looking at 10% of the LEL. You are only at 10% of the lower explosive limit. And as you go in there, further in the room, it goes up and up and up and up and up. When it gets to 100% on an explosimeter, what that means is you are now at 100% of the LEL. In other words, you are now entering an explosive atmosphere. I used to do a lot of training for the firemen, and sometimes you say, no, I'm not interested. They're the ones going in. They need to know that. That's what it means. 100% does not mean 100% acetylene. It means you are at 100% of the LEL. You are now in an explosive atmosphere. So these are the definitions. Flash, LEL, UEL, etc. That completes this section of this element.